The first wave of generative AI was, of course, defined by the chat interface. Now, this wasn't a mistake. It was a completely necessary but ultimately temporary developmental stage. It was our first real way to interact with raw intelligence, but it was never the final form. You see, chat's primary purpose was exploration and discovery. It gave us a handle on what these models could actually do, a way for us to probe their reasoning and test their limits, all using the most natural interface we have, language. And that really reveals the core architectural truth here. Chat functioned as a REPL, a read, evaluate, print loop, for intelligence. It was absolutely invaluable as a learning tool, but its very design was structurally incapable of supporting the kind of autonomous, reliable, and accountable systems that production environments demand. The industry, well, it had to move on. So, in this explainer, we're going to trace the 6 critical stages of this architectural shift, from what was a simple interface to what is now complex, governed infrastructure. First, we really need to frame the chat paradigm using a concept that's familiar in computer science, the REPL. This is really the key to understanding both why it worked so well at the beginning and why it was always destined to be replaced. A REPL, of course, is an interactive shell. You enter a command, you observe the result, and then you iterate. It's designed for experimentation, for that rapid feedback you need during development and research. What it's not designed for is robust, safe, or correct operation inside a production system. And the chat box was, in effect, the world's largest REPL. And just like any REPL, it operated on a set of hidden assumptions. It always assumed a human was in the loop to provide memory and context between turns, to notice and correct the model's mistakes, to judge which suggested actions were safe, and to resolve any ambiguity. Of course, these assumptions completely collapse the moment you require true autonomy. This brings us to the first major architectural failure of the chat model, its complete inability to manage state. This is really where that illusion of memory began to break down under real-world pressure. Expanding the context window gave us an impression of memory, but it was a fragile illusion. Context is ephemeral, it's session-bound, and it's completely ungoverned. It provides recall, sure, but not durable state. And as prompts grew longer, systems began to suffer from context sprawl, where the original instructions, the conversation history, and the actual goals would just blend together into this ambiguous, unpredictable mess. So the crucial shift was in system design. We moved from that prompt-driven flow, that single vertical column of text, to a state graph flow. Instead of a linear conversation, agentic systems operate on a graph of discrete, verifiable states like planning, executing, and verifying. The system transitions between these states based on defined events, not on some linguistic inference. This was the move from improvisation to actual engineering. Next, we have to talk about the critical gap between language generation and real-world impact. See, chat systems generate text, production systems have to take action, and this is where we run headfirst into the problem of side effects. This is the canonical failure mode that plagued early agentic prototypes. An agent tries to perform an action, say submitting a payment. The API times out. The agent, misinterpreting that timeout as a failure, just retries the request. And the result? The customer gets double charged. This wasn't some rare occurrence. It was a deep, systemic flaw. And it's so critical to understand that these were not failures of the model's intelligence or its reasoning. They were fundamental architectural failures. The system simply was not designed to safely manage actions that have irreversible consequences in the real world. The architectural principle that solves this is idempotency. An idempotent operation ensures that performing an action multiple times has the exact same effect as performing it just once. For any system that takes autonomous action, sending an email, modifying a database, charging a card, idempotency is not optional. It is existential. So, how do we build systems that can actually act safely? Well, this is where the agentic control system comes in. It's a set of architectural patterns specifically designed to impose discipline on probabilistic intelligence. At its core is a control loop. Observe, reason, and act. But it's a mistake to think of this as the agent's brain. It's actually a disciplined control pattern that's embedded within a much larger system. The system makes sure that observations of the environment are structured, that reasoning only generates a proposed action, and that the action is only executed after it passes a series of validation checks. Now, this loop depends on what we can call system integrity mechanisms.
First, typed observations. An agent has to be able to distinguish between, say, a record not found error and a service unavailable timeout. If the observation is wrong, the entire reasoning process collapses. Second, the execution itself must be isolated. Modern systems use ephemeral compute. Disposable WASM runtimes are micro VMs that are created for a single task and then immediately destroyed, containing all possible risks. The next stage in this whole evolution was the realization that a single monolithic agent was just a flawed concept. Just like in mature software engineering, the solution was decomposition and a clear separation of concerns.
Think about it. A single agent that plans, executes, and then verifies its own work is just prone to self-justifying failure loops. So modern systems separate these roles. You have a planner agent, an executor agent, a verifier, and an observer. Each one has limited authority and is independently auditable. This separation of concerns proved to be far more robust than just trying to amplify a single agent's intelligence.
And this led to a completely new coordination pattern. Early multi-agent systems used a simple conversational handoff model, basically a linear chain. It was incredibly brittle. So the industry shifted to what's known as a blackboard architecture. Here, agents don't talk to each other directly. Instead, they post their findings to a shared, structured state, and other agents subscribe to updates. Coordination is achieved through state synchronization, not dialogue, which is far, far more resilient.
This brings us to the final evolution, the changing role of the human. The human didn't disappear from the loop at all. Their position just shifted, from being a conversational partner to becoming the system governor. Humans stopped chatting with the AI and started governing its actions. The interface changed from a chat box to a dashboard of intent. The human now stands at an approval gate for high-risk actions, reviews proposed changes in a diff format, and relies on immutable audit trails for accountability. The human is no longer the memory. The human is the final authority.
And this really illustrates why the shift was irreversible. Once production systems began to require these features, durable state, idempotent actions, isolated execution, and formal approvals, there was just no going back. The chat paradigm was architecturally incapable of providing any of these guarantees.
So we no longer ask what a model knows. We now ask what the system is authorized to do, under what conditions, and with what safeguards. This is the moment AI stopped being a novelty interface and became a true piece of infrastructure.
This whole transition wasn't a rejection of intelligence, but really the maturation of it. We now have these probabilistic cores governed by deterministic shells. And that leaves us with the next critical question. As these agentic systems proliferate, what new control stacks and protocols will we need to manage these emerging systems of systems?